Do you trust your cryptocurrency wallets? Have you ever seriously thought about how secure they really are? Do you use the standard 12-word seed phrase or perhaps the 24-word version? Maybe you have been adding even a 25 custom word for extra security. If you have ever come across forum posts where people complain about their funds disappearing from their wallets, even though they live alone and have securely stored their seed words, you'll notice that almost all of the replies suggest that the person must have somehow compromised their seed words. No one questions whether the funds might actually have disappeared. Imagine if someone broke into your house and stole your money, and when you ask in a forum about that situation, everyone blames you for leaving the door unlocked. That would be incredibly frustrating. You've probably read that the cryptocurrency wallets are extremely secure and that the number of combinations needed to crack one specific wallet is astronomical. And that is true. But of course, if you replace the sentence "number of combinations needed to crack one specific wallet" with the sentence "number of combinations needed to crack any random wallet", that number is less astronomical. To have a wallet, you first need a private key, which is a random string with specific characteristics. From that private key, the wallet address is generated, but in a way that can be reversed. In other words, if you can always derive the wallet address from the private key, but you can never figure out the private key just by knowing the wallet address. For most people, the challenge is storing and memorizing a private key without making a mistake or forgetting it. That's why not many people generate a purely random private key. Instead, they use a sequence of 12 or 24 chosen words or simply random words. From these 12 or 24 words, a private key is generated using standards like BIP32 or BIP44. This private key allows for the derivation of multiple public keys or addresses for different cryptocurrencies, following protocols such as BIP44 or BIP49. The private key must be kept secret, as it is the basis for all addresses and access to the funds. Writing down or memorizing just 12 or 24 words is easy for humans, should be, which is why it's common to use that specific set of words to generate the private key, and then the wallet is derived from that private key. This method is great for memorizing and securely storing the way to access your wallets. But everything has its weak points, and the weak point here is that while the universe of purely random private key combinations is immense, the set of private key derived from combinations of 24 words is much smaller, and it's even smaller if you use only 12 words. If your wallet, created using 12 words, has an address like this one, and someone tries to guess all the possible combinations of 12 words to reveal your private key, they would need an enormous amount of computing power and time. But if your wallet address is this one, something like this, and someone tries to guess all the possible combinations of 12 words to reveal your private key, they will never succeed. Why? Because this wallet was created using 24 words. So, using only 12 words, you will never be able to derive the same private key. If your wallet created using 24 words has the address like this, and someone tries to guess all the combinations of those 24 words to reveal your private key, they would also need an enormous amount of computing power and time. And if your wallet address is something like this, and someone tries to guess all the combinations of 24 words to reveal your private key, they will never succeed. Why? Because this wallet was created using 25 words. So, using only 24 words, they will never guess the same private key. If someone generates a purely random private key, it could belong to any group in the full universe of private keys. It might be in the 12 words universe or in the 24 words universe. It's clear that trying to figure out a private key from a specific wallet address is extremely complicated, at least for nowadays. However, we need to remember that out of the immense universe of all possible private keys, there are already millions of wallets in use. If the goal is to randomly guess a private key, not a specifically targeted one, but any from the millions of wallets already active, the complexity is still significant, of course huge, but its complexity decreases over the time as the number of wallets in use continues to grow. In other words, trying to figure out which 24 words would generate the private key for a specific address like this, generated with 24 words, is incredibly difficult. But we also have to take into consideration that the computing process of generating just a random private key and then checking if the corresponding wallet is already in use is an extremely fast and simple process. A similar situation arises when you lose some words from your wallet seed phrase. If you've lost just the 24th word, the last word, it's very easy and fast to recover your wallet. You only need to try the 2048 official words from the dictionary used by your wallet provider. If you've lost the last two words, you simply need to check about 4 million of combinations. That is still quite manageable. Even if you've lost the last three words, it's not a major problem as long as you use parallel computing or distributed computing frameworks like could be, for example, Dask with Python. How would you approach it? How would be the process? Okay, first you should use a secure environment or a disposable container because you will be handling 20 something words that you do not want to compromise. And of course, you should remain offline. In this example I'll show you later, we use a specific version of Python and some cryptographic packages to generate the missing word combinations as fast as possible, using as many CPU cores as available. You should create an identifier to keep track of each combination and continue distributing them in batches across your CPU cores. At this point, if you've only lost one or two words, you can simply generate the private key for each combination, derive the wallet address from the private key, and check if it matches your lost address. If it does, you are done. But if you have lost more than two words, or you are unsure of the exact position of the missing words, or for any reason the number of combinations you need to check becomes very large, you will need to track your progress. You'll want to be able to stop your computer at some point and resume later without losing any data or having to repeat large amounts of combinations. To achieve this, in order to store the combinations locally as fast as possible, you'll need to use a database like PostgreSQL because it can handle asynchronous operations using AsyncPG. Additionally, PostgreSQL supports parallel query execution, meaning that you can insert data from multiple cores working in parallel. Each core can insert data asynchronously, which means the code running on each core won't be paused while waiting for database responses. Instead, it will continue managing other tasks while waiting for the database, improving efficiency. In this setup, we'll have two distinct blocks of code that require different packages and possibly different versions of Python. Therefore, we'll need to write them separately and find a way to make them work together. One option is that once the first block has generated a batch of addresses to store, it could communicate with the second block via fast API, for example, triggering the necessary queries to insert the data into the database. The drawback of this approach is that if you leave your computer running and it crashes at some point, no further work will be done after that point. So I would prefer to set up a different approach that is easier to implement and keeps the processes of generating wallets and storing them in a database completely separate. This can be done by using intermediate storage. For example, you could have a folder called created wallets, and if you want an additional layer of persistence, another folder called safely stored wallets. The first part of your code would simply generate and store CSV files in the created wallets folder. Its only task is to create files with wallet data and save them there in the folder. The second part of your code will take files from this folder, store the wallets in the database, and if no errors happen occur, move the process's CSV file to the safely stored wallets folder. This way, if you leave your computer running for a long time and one process fails, at least the other one will continue doing useful work. To increase security, you can store all your data in an encrypted folder. For instance, you could use Cryptomator, Veracrypt, or a trusted online encrypted storage service to manage your files. Finally, you only need to periodically query the database and check if you've successfully recovered your wallet. And so, that would be the process for recovering your wallet. It could take weeks, months, or even years. Or maybe, since it's a random guessing process, you might get lucky and recover it in just a few seconds. Who knows? When you engage in a process like this, it makes you think about how secure your wallets really are. Of course, as we mentioned before, pinpointing a specific address and trying to guess its private key is virtually impossible, at least for the average person, even with a significant computing power. But the fact that randomly guessing wallets and checking if they are in use is such a easy process makes me personally think that it might be a potential risk if you do not take some extra measures. It's easy to Google how secure wallets are and see the vast number of possible combinations for a 12-word wallet. Each word comes from a list of 2048 possible words. There are, so, 2048 to the power of 12 combinations, which equals, okay, this huge number of combinations. And yet hundreds of millions of wallets are already in use. But to truly understand from your own experience how secure wallets really are beyond just seeing a large number of possible combinations, the best approach would be to simulate a brute force attack on a regular computer, where we know the processor, the number of cores, and frequency. This way, this way we can estimate the system's attack capacity for a given time frame and specific computational power. This would provide a real-world number representing the actual attack capacity. That number will likely be minimal, almost insignificant. However, by having this number, we can then calculate how much we would need to scale up our computing power to achieve a minimal effective attack capacity. What exactly does that mean? Imagine someone tells you that they have developed a cipher that's hard to crack, and you would need to try 5 million combinations to break it. That might sound secure in numbers, but if you can generate only 100,000 combinations using one core at 1.2 GHz, it means that with a 32-core Threadripper, you might need only about a few days to crack the entire cipher. So, now you have a first-hand experience on how secure that cipher really is. So, how can we get a first-hand perspective on how secure wallets, crypto wallets, really are? Let's try some Python code optimizing the process as much as possible by using parallel execution and asynchronous execution whenever we can. Here is the code we are going to use. So this is the code we are going to use. We use the Python's concurrent features module to parallelize a task using multiple processes. The function we are going to parallelize is called core walls creation, and this is a function that just creates a fully random private key, and from that private key it derives the corresponding wallet. Then we iterate over the tasks as they complete, and we collect the results. For example, let's say that we choose here to use as number of cores 2, and we want to create just 2 wallets. So we are going to have two CSV files, each CSV file created by each core of the laptop. Let's execute this. I'm going to save. And let's take a look at the folder where the CSV files will be created. Okay, let's execute this. So here we've got two files created, one file with each core. If we take a look, here we've got two new wallets, one in this file and another one in this file. We can check that they are really real wallets. We can do it just using, for example, Etherscan. In Etherscan, we can input this address, and you can see that this is of course a real address, of course never used. And if we want to check that the process of derivating the address from the private key is correct, we can also do something here that is opening the wallet in a very unsafe way. That is just inputting the private key. You can see that here we've got the same wallet 0x056FA as here. So you can check that the process is working. And the same with this other address. So now we've got a working process of generating random private keys, and from that keys derivating the wallet address. And of course, as we are not interested at all about the private keys, let me just permanently delete everything. Okay, I delete this, and let's delete these files permanently. Yes, of course. So I will delete the part of storing the private key because we are not interested at all about the private key. And instead, we are going just to store a random character list just to simulate the process of storaging in the CSV file. Okay, I save. And now let's check if it's working correctly as we want. Here is our empty folder. Let's execute again after saving. Okay, you can see here we've got as private address something random, not random, but it's going to be all time the same non-functional private key. So we don't want to play with this. Just is for testing speed tests. And so let's try to increase and make some tests. If we want to generate, for example, 2000 wallets with one core, let's see how much does it takes for us. Let's execute. You can see that the new file is created here with 2000 wallets. The private key was not stored because we are not interested at all on this. And we can see that for generating in a completely correct way 2000 wallets, we just need 1 second, 0.2, using only one core. Let's see how much can we speed up this process. For example, if we choose instead of 2000 wallets, let's generate 20,000 wallets using, for example, 5 cores. Save. Let's execute. You can see that here new files are here. We've got 1, 2, 3, 4, 5 new files, and each file is containing 4,000 new wallets. When we start the process, we've got 4,000 wallets created with one core, with another core, another 4,000, and with 5 cores. Each core creates private keys, forgets about the private key, just store these characters, and generates a wallet. How long did it take? It take about 3 seconds. You can see that as you keep on parallelizing, you can increase heavily the process and still having a good amount of speed. The next step will be a separate process that retrieves a list of files stored in the previous folder and inserts them into a PostgreSQL database. If the process completes without any errors, we can either move the files to a new folder or just delete them, depending on our preferences. Of course, we have a Docker PostgreSQL container running, with our folder on the laptop mirrored to the appropriate folder inside the container. We are also mirroring our laptop's port 5432 to the PostgreSQL standard port inside the container, the port 5432. Now let's take a deeper look at this process. We choose the number of cores and trigger the main function. The main function then triggers another function, which we'll use to retrieve the file names from our folder and select as many files as we have cores. This way, each core on our machine will process just one file. Next, we move into the process pool executor, where we want each process to execute some asynchronous code that will query the database asynchronously to insert the data as quickly as possible. This is the synchronous code we want to run on each core. Each core will open its assigned file, extract the data, connect to the database, and save the data inside the database. The issue is that we cannot directly assign asynchronous functions to a process pool executor because it only accepts synchronous functions. The solution here is to use an intermediate synchronous function, a normal function, a helper, which will be the one distributed to the process pool executor. When these synchronous functions are running in parallel on independent cores, they will trigger an asynchronous run to execute the asynchronous function that will query the database asynchronously. So, let's test the code with just one core and see what happens. Now you can adjust parameters from both processes, such as the number of wallets to create per CSV file and the number of cores to allocate to each process, so you can balance the workload and optimize the overall performance. And since this is all about maximizing parallel and asynchronous processing and squeezing as much performance as possible from your machine's cores, we can add another process to interact with the database. You can also check if your lost wallet is among the generated wallets, or you can even check the balances for the generated wallets. For doing this, you can use a EVM provider like Infura or Alchemy, or a blockchain explorer like Etherscan. Since web requests through APIs will be the slowest part of the process, you can speed it up by using multiple services with several accounts and distributing your queries across all of them. So here is the code for doing that. We have a configuration file with 4 API keys, and the more API keys you have, the faster the process will be. Next, we have an asynchronous function that makes an asynchronous call to Etherscan using one specific API key, requesting the balances for 20 addresses at a time. We trigger this function asynchronously for each API key, ensuring that none of them block the Python GIL, the global interpreter lock, while waiting for a response. Then we have another asynchronous function to update the values in the database. Now let's take a look at the main function to better understand the whole process. First, we connect to the database and retrieve a batch of wallet addresses. Then, we create a large array with chunks of 20 wallets each. Then, we want to use our 4 API keys to check all these batches of 20 addresses, and there are several ways to do that. We could use the concurrent module with a thread pool executor, or we could use a pool of asynchronous tasks and manage them with a semaphore to control how many tasks we want to run concurrently. I'm going to use a more custom approach. I will set a pointer at the beginning of our tasks and define a step value, let's say 5. This way, we will move through the entire array of tasks, assigning 5 of them, one step, to each API. 5 tasks to the first API. We move another 5 tasks to the second API and so on. Once each API key has 5 tasks assigned, we can launch the tasks asynchronously and wait for the results. Of course, we will launch the tasks inside a client session and keep on doing that while our pointer doesn't reach the end of the tasks array. In this approach, instead of introducing a useless pause before the next request to avoid being banned by Etherscan or running a large process controlled by an asynchronous semaphore, we can pause the requests while organizing the partial results returned by Etherscan. So, while giving some rest to the API calls, we can do something more useful than just waiting. We will use that pause to gather the partial results from this first pass into an array, which will then be reset and store the partial results in a total results array that grows with each pass. When we finally complete all the passes, we store the data from the total results array in the database. Let's take a look at this in action. Let's take a look at all the three processes working together, utilizing different cores and maximizing each core's performance asynchronously whenever it's possible. When combined all together, you can see the enormous number of wallets we can generate in a short amount of time on a simple laptop. From this, we can make some calculations to estimate how many wallets could be generated and even checked using a simple and cheap 32-core second-hand CPU, while also considering the cost of an EVM subscription to check thousands of addresses in a single API call. Of course, we will never be able to generate enough wallets to pose any real risk. But it is also true that explanations you often hear about how it could take thousands of years to find a specific wallet in the vast universe sounds less convincing when you consider that, with a bit of luck, it might only take a few minutes. Now let's try to find a real world analogy for the concept of randomly generating a private key and storing your valuables there. Imagine a huge country where no house or room has any doors to prevent intruders from entering. If you want to store your valuables, you simply choose a random region, a random city, a random street, random building number, random floor, and random room number. You write down those selections on a piece of paper to feel secure that you will never lose your valuables. And you keep that piece of paper very safe and hidden, believing that no one will ever steal from you. Well, do you see anything strange about that concept, about that idea? Actually, I would only trust that concept as an experiment to see how well it works. But if I truly wanted to feel secure with the idea of protecting valuables, I would want the option to add my own protective door to the room I choose, a door as secure as I believe it's necessary, just to be sure that no one accidentally steps into my chosen room. Wherever you choose for your wallet, whether it's 12 words plus a long 13th word or 24 words with a random 25 extra word, your wallet is still part of the universe of purely random wallets. That's the reality, like a room in our example that can potentially be found by accident. It would be great if EVMs, the virtual machines, could implement a feature where for every wallet, the first transaction made to that wallet allows you to insert an encrypted password, as short or long as you want. It could even be encrypted personal information like your name or your ID. This would be useful even in the future if you ever need to prove the ownership of the wallet for legal reasons. These are just some brainstorming ideas. As of now, one of the most secure ways to prevent access to your assets stored on a blockchain by pure random luck is a multi-signature wallet. How can we visualize this in our real-world example of the huge city with open doors? Well, imagine you store your valuables in a random room in a huge country with no doors, but with a digital condition. The condition that you can only move your valuables using a tool stored in another randomly selected room within the same city. So, someone could, by luck, find the room with your private key and all your valuable assets, but even then, they wouldn't be able to access them without also finding the second random room in the huge city that represents the second signature of your wallet. A simple and human manageable way to think about this would be to securely store and memorize your 12-word wallet and then use the same 12 words with an additional 13 large words, could be your encrypted name, to create another wallet that serves as a multi-signature partner to the first one. That extra 13 words, despite of being really large and random looking, will be for you something really easy to reproduce because it's some of your personal information encrypted.